In this lecture, we continue our discussion on the queuing models, and we continue our discussion on the MMC infinity model, where we have multiple servers and we have an infinite queue length. In the earlier lecture, we derived some equations. We derived this expression for Pn, probability that there are n people in the system, as lambda by mu to the power n by n factorial p naught when n is less than c, and Pn is equal to lambda by mu to the power n divided by c factorial c to the power n minus c p naught when n greater than or equal to c. This has infinite queue length. So, p naught plus p 1 plus p 2 up to p infinity equal to 1 gave us this equation, p naught is equal to 1 by sigma n equal to 0 to c minus 1 rho power n by n factorial plus rho power c by c factorial 1 by 1 minus rho by c. This was an infinite geometric series. This has as many terms depending on the number of servers. So, this will have 0, this will have exactly c terms from 0 to c minus 1. Now, once we get an expression for p naught, we need to derive expressions for Ls, Lq, Ws and Wq. For multiple server models, it is customary to define Lq first and get an expression for Lq, from which we would get expressions for Ls, Wq and Ws. So, if we derive the equation for Lq, we would get Lq is equal to sigma n minus c p n equal to c to infinity. The queue is actually 0 when we have c people, the queue length is 1 when we have c plus 1 and so on. So, n minus c into p n would give us the corresponding expected length of the queue. Now, we need to substitute these expressions for p n into this and we will get, so Lq is equal to, this is sigma j equal to 0 to j equal to infinity, j p n plus j, j p c plus j. So, the queue actually starts when n is greater than or equal to c. So, we do not require this expression to get Lq, it is enough if we use this expression to get Lq, because here c to infinity has been substituted by 0 to infinity, where j equal to n minus c. So, j equal to 0, 1, 2, 3 would mean n is equal to c, c plus 1, c plus 2 etc. So, it is enough to use this expression. So, this will be equal to sigma j equal to 0 to infinity j lambda by mu to the power n rho power n by c factorial c to the power n minus c So, p probability that there are c plus j people in the system would give j rho to the power c plus j divided by c factorial into c to the power j p naught. Now, this comes because the general expression for p n is rho to the power n by c factorial c to the power n minus c. So, now n becomes c plus j. So, c factorial remains here. So, lambda by mu to the power c plus j is rho to the power c plus j. Now, when n is equal to c plus j minus c would give only j. So, c factorial c power j p naught. Now, from this we can write this as, here we will pull out rho power c plus 1 such that we will get j rho to the power j minus 1 here divided by c factorial. We also need, here we have rho to the power j minus 1. So, we need c to the power j minus 1. So, we pull out another c here, c factorial into c into p naught by c to the power j minus 1. The summation actually comes outside here. So, the summation will come here. Now, this is rewritten as, now we pull out some of the common things. So, rho to the power c plus 1 divided by c factorial into c comes out, p naught also comes out, sigma, we have j rho by c to the power j minus 1, which is d by d rho of rho by c to the power j. Now, d by d rho of rho by c to the power j would be j rho by c to the power j minus 1 into 1 by c. So, we will have a c factorial now d by d rho of rho by c, this is d of rho by c, d by d rho by c of rho by c to the power j. So, this will be j rho by c to the power j minus 1. So, we have j rho by c to the power j minus 1. Now, we remove the differentiation and the summation to the other side. So, we get rho to the power c plus 1 p naught c factorial into c to d by d of rho by c sigma rho by c to the power j. Now, this is an infinite geometric series. So, this is rho to the power c plus 1 p naught by c factorial into c d by d of rho by c. This will be 1 plus rho by c plus rho by c the whole square and so on. So, it is an infinite geometric series with first term equal to 1, common factor being rho by c, and we know that rho by c is less than 1 when we have an infinite Q length model. So, we can use the infinite geometric series formula to get 1 by 1 minus rho by c. Now, we can differentiate this with respect to rho by c to get LQ is equal to rho power c plus 1 p naught by c factorial into c. This will become minus 1 by 1 minus rho by c the whole square into minus 1. So, we get plus 1 by 1 by 1 minus rho by c. We are differentiating with respect to rho by c. So, this is like d by dx of 1 by 1 minus x. So, 1 minus x will give minus 1 by x square, and then you get another minus 1 that comes here. So, we will get plus 1 minus rho by c the whole square. This on simplification would give us rho to the power c plus 1 p naught by, this is c minus rho the whole square. We take a c square outside. So, one c will get cancelled here and one c will go here to get c minus 1 factorial into c minus rho the whole square into p naught. So, this is the expression for LQ when we have an MMC infinity infinity model. And once we know LQ, then we can go back and derive expressions for LS, WS and WQ using the earlier equations that we have derived for using the Little's formula. So, once we know rho and c, we get the expressions for P naught which were derived earlier, from which we can get an expression for LQ, and then using the Little's formula we can go back and get LS, WS and WQ respectively. Now we take a numerical example to try and understand how these values effectively look like. Now let us have a multi-facility system where we have C equal to 2. Let us say we have typically like a web browsing center with 2 terminals. Let us say people arrive with lambda equal to 10 per hour, and the effective service rates are such that we have mu equal to 6 per hour. Now this would give us lambda by C mu is 10 by 12, which is 5 by 6, which is less than 1. So lambda by C mu is less than 1. Now let us find out the values. Now P naught is equal to sigma rho power n by n factorial plus rho power C by C factorial into 1 by 1 minus rho by C. So this is what we derived as the expression for P naught, in inverse of this 1 by sigma rho power n by n factorial rho power C by C factorial into 1 minus rho by C. Now this would give us, this sigma is from 0 to C minus 1. So when n equal to 0 we get, or on expansion we would get, this has 2 terms because C equal to 2. So for n equal to 0 and for n equal to 1. So this would give us 1 plus rho power n by n factorial, rho is lambda by mu. So lambda by mu is 10 by 6. So these are the 2 terms corresponding to this, plus rho power C by C factorial, which is 10 by 6 the whole square into 1 by 2, C being 2, C factorial is 2, into 1 minus 1 by 1 minus rho by C. Rho by C is 5 by 6, so 5 by 6. Now this term is 1 by 6, we can simplify this to get P naught is equal to, so this is 1 plus 10 by 6 plus, this is 100 into, here we have 1 minus 5 by 6 is 1 by 6. So this will go to the other side. So into 6 by 36 into 2 inverse. So this will go 6 times. So this will, this on simplification would give us P naught equal to 0.0909 that we have here. So P naught is equal to 0.0909, and once we know P naught we can calculate P1, P2 or any other number that we would like to do, and once we know P naught we can actually find out the rest of them. If we want to know that, the first question that we may look at is, what is the probability that both the computers are free when a person arrives, which means when a person arrives the entire system is empty. So P naught is when there is nobody in the system. So both the computers are free when the person arrives is given by 0.0909. The next one is, what is the probability that a person who comes gets a computer. Now there are 2 computers, so a person who comes will get a computer when both are free or when one is free, which means that will be equal to P naught plus P1. In this case it will be P naught plus rho P naught. because we have n equal to 1. So, we will simply have rho power n by n factorial. So, rho power 1 by 1 factorial into P naught. So, that will become P naught plus rho P naught. Rho in this example is rho is 10 by 6 and rho by C is 5 by 6, which is less than 1. So, this probability will be, this will be P naught plus 10 by 6 P naught, which is 16 by 6 into 0.0909. Another question would be, what is the probability that there is no Q? So, there will be no Q when either there are 0 people in the system or 1 person in the system or 2 people in the system. So, probability that there is no Q is given by P naught plus P 1 plus P 2. So, this is probability that person gets a computer or gets a server. This is probability of no Q. So, this will become P naught plus P 1, or P 1 is rho P naught So, this will become rho P naught, this will become rho square by 2 into P naught, because P 2 is rho square by 2 factorial, which is rho square by 2 into P naught. So, we can substitute for P naught and rho square by 2 to get such a probability. Now, what is the expected number in the system? So, in order to find Ls, we first need to find Lq. Lq is given by this formula, rho power c plus 1 by c factorial into c to 1 by 1 minus rho by c the whole square. Now, we know that rho is equal to 10 by 6, c is equal to 2. So, substituting here, we would get Lq will be 3.7878 if we substitute here, and then Ls will be Lq plus rho. So, this will become 3.7878 plus 1.666, which will become 5.4544. We may also find out Wq and Ws. For example, Wq in this case will be Lq by lambda, which will be 3.7878 by 10, which will be 0.378 hour, which is roughly 22 minutes. So, like this we can work out the computations to get the values of Lq, from which Wq and other expressions can be found out. Now, the only subtle difference here is that when this is an infinite Q length model, we have added one more server into this. So, C is equal to 2. So, if we compare the old values of P naught, now because we have more servers in the system will be idle much more than it was in the earlier model. In the earlier model, we used 5 by 6, lambda was 5, mu was 6. Now, we have a system where lambda is 10, c is equal to 2 and mu equal to 6. So, effectively lambda by c mu turns out to be 5 by 6. So, when we have multiple servers, it is only understandable that the system having more servers will have more free time available, system would have more free time available. At the same time, it will be much more friendly towards the end user, where Ls, the length of the system, and Lq will reduce considerably compared to what it was in the earlier case. The earlier case, Ls was around 8, Lq was around 7. Now, we realize that Lq is just about half of 7, or little more than half of 7. So, LS and LQ would come down as the number of servers increase. The next model that we will see, which is the fourth model, is when we restrict this to n. So, when we restrict this to n, we look at the fourth model. Now, the model becomes the arrivals follow a Poisson distribution of lambda per hour, service times are exponential with mu, we have C more than one server and finite queue length of not more than n. Therefore, in this system we will only have 0, 1 up to n people in the system. It is also fair to assume that this n will be greater than C. So, we will have a system to find out P naught, we will require P naught plus P1 plus P2 plus Pn is equal to 1, and we also know that up to C the Pn expression is different and C and above the Pn expression is different. So, this will give sigma n equal to 0 to C minus 1 rho power n by n factorial P naught plus sigma n equal to C to n rho power So, this will be n equal to C to n rho power n by C factorial C to the power n minus C P naught is equal to 1. Now, this comes because when n is greater than or equal to C, then the effective service rate will be up to mu 2 mu up to C mu. So, 1 into 2 into 3 up to C will give us the C factorial, after which it will always be C mu. So, we will get C to the power n minus C and rho to the power n into P naught. So, this on summation would give us a final expression for P naught, which will be like this. Now, this will give us P naught into sigma n equal to 0 to C minus 1 rho power n by n factorial plus, when we expand this we will get, we can take a rho power C outside. So, this will become rho power C by C factorial P naught sigma this will become rho by C to the power n minus C. See, the C factorial remains as C factorial, P naught comes here. Now, since we have C to the power n minus C, we take a rho power C outside, so that it becomes rho by C to the power n minus C. This is from n equal to C to n. So, this would give us P naught into sigma n equal to 0 to C minus 1 rho power n by n factorial plus rho power C by C factorial P naught into now, when n equal to C we get 1, when n equal to C plus 1, when n equal to C we get 0, when n equal to C plus 1 we get 1 and so on. So, this will become on expansion 1 plus rho by C plus rho by C the whole square plus. Now, this is from C, C plus 1, C plus 2 up to n. For example, if C equal to 2 and n is equal to 8, we will have 2, 3, 4, 5, 6, 7, 8, which are 7 terms. So, effectively this will be rho by C to the power n minus C plus n minus C. First term, second term, third term, this will be the, if C equal to 2, for example, if C equal to 2 and say n equal to 8. So, when C equal to 2, this will be the term. For C equal to 3, it will be rho by C. For C equal to 4, it is rho by C the whole square. So, for C equal to 8, it will be rho by C to the power 6, which will be rho by C to the power n minus C. Now, this is again a geometric series, but it is a finite geometric series. So, this on summation would give us P naught into sigma rho power n by n factorial plus rho power C by C factorial plus rho power C by C factorial. This is a finite geometric series with n minus C plus 1 terms. So, this will become 1 minus r to the power n by 1 minus r to the power n plus 1 by 1 minus r. So, this would give us into 1 minus rho by C to the power n minus C plus 1 by 1 minus rho by C is equal to 1, from which P naught is equal to sigma rho power n by n factorial plus rho power C by C factorial 1 minus rho by C to the power n minus C plus 1 by 1 minus rho by C, the whole thing inverse. So, once we get an expression for P naught, we can calculate for any P n. If n is less than or equal to C, we can use this part, and when n is greater than C, we can use this part to get any P n. So, the only other thing that we need to do is to get Ls, Lq, Ws, Wq. We also have the possibility of forced bulking, because we have a finite q length of n. So, as people get into the system, if they find that already there are n people there, then they leave. So, we need to first find out P n. P n would come from here. So, P n will be rho to the power n by C factorial C to the power n minus C into P naught. Now, P naught is known, rho is known, C is also known, n is known. So, we can calculate P n. Now, this is the probability that there are n people in the system. So, this is the probability that someone who comes into the system will not join and leave the system due to forced bulking. Then the next thing we need to do is to get an expression for Lq and then try and get expressions for Ls, Wq and Ws. So, the expression for Lq would look like this. So, we would say Lq is the expected length of the queue. So, Lq in this case is given by n equal to C to n minus C P n. So, when the system has C people, the queue length is 0, system has C or less people, the queue length is 0, and the queue builds only when the number in the system is greater than or equal to C. So, we start from C equal to n to get this. So, P n now will always have n greater than or equal to C. So, we will write the second term. So, this will become n equal to C or j equal to 0 to n minus c j p c plus j. Now, this will become sigma j equal to 0 to n minus c j. Probability that c plus j people are there in the system is rho to the power c plus j divided by c factorial c to the power n minus c, which is c to the power c plus j minus c. So, c to the power j into p naught. Now, again we will have to come back and pull out a few terms. So, this will become, since there is a c power j and there is a rho power c plus j, we take a rho power c outside. So, this will become rho power c p naught by c factorial then we write this in the form j rho by c to the power j minus 1. So, we take another rho by c outside, so that this becomes rho power c plus 1 p naught by c factorial into c sigma j rho by c to the power j minus 1. Now, this will be written as rho to the power c plus 1 p naught by c factorial into c sigma d by d of rho by c into rho by c to the power j. Now, again we switch the differentiation and the summation to get rho power c plus 1 p naught by c factorial into c d by d of rho by c into sigma rho by c to the power j, except that we have to carefully define the summation. So, j equal to 0 to n minus c. Now, again continuing, we would get now from this L by LQ will become so LQ will become, now writing this rho power c plus 1 p naught by c factorial into c. This is a finite geometric series. When j equal to 0, this is 1. So, 1 plus rho by c plus rho by c the whole square up to rho by c to the power n minus c. So, we use the finite geometric series expression to get 1 minus rho by c to the power n minus c plus 1 divided by 1 minus rho by c. Of course, we need to do d by d of rho by c. Now, this would give us a reasonably complex expression. This is a u by v formula. So, we need to use v du minus u dv by v square. I will just show one more expansion of this and then we will write the final expression. So, this will be rho to the power c plus 1 p naught by c factorial into c. This is like 1 minus rho by c. So, this is divided by 1 minus rho by c the whole square. Remember, you are differentiating with respect to this. So, v du 1 minus rho by c into differentiation of this. So, this will go. So, this will become n minus c plus 1 rho by c to the power n minus c with a minus sign. So, we just need to carefully put a minus sign somewhere. This is a minus sign, it is not minus, it is a minus sign that comes in. So, I will possibly do this with a minus sign, minus this is v du minus u dv. So, 1 minus rho by c to the power n minus c plus 1 into d of this. So, this will become rho by 1 minus 1 differentiation of this with respect to rho by c will simply become, this is like differentiating 1 minus x with respect to x. So, we get a minus 1 here. So, this becomes plus 1 into P naught. This can be easily simplified. So, this will give us the final expression, which is rho power c plus 1 P naught by c minus 1 factorial. That comes in because when we expand this, we can do a c minus rho the whole square, c square will come to the numerator. When c square comes to the numerator, one c will go and the c factorial will become c minus 1 factorial into this expression will be 1 minus rho by c to the power n minus c plus 1, which comes from here, minus n minus c plus 1, which comes from here, into 1 minus rho by c into rho by c to the power n minus c, and the whole thing divided by c minus rho the whole square, which comes out of this. So, this is the final expression for LQ when we use an MMC n infinity model. So, once we get this expression for LQ, we can also get WS, WQ and so on. These two are two computers and 7 people in the system, which means there are 5 other chairs which are available. Now, the probability that a person who comes in immediately takes a computer will be P naught plus P 1 when there is at least, when it is P naught 2 computers are available, P 1 1 computer is available. So, this will become P naught plus rho P naught, and this on substitution would give us 0.3248. So, there is a probability of 0.3248 that a person who comes immediately can get a system. Now, probability that there is no Q on arrival is P naught plus P 1 plus P 2, because even if there are 2 people in the system, both these people are actually using the computer. So, there is no Q. So, probability that there is no Q is P naught plus P 1 plus P 2, and this will be 0.3248, which is P naught plus P 1 plus rho square by 2 P naught, which on simplification would give us 0.4939. So, probability that when a person comes in there is no Q is 0.4939. Probability that when a person comes in the person can directly take a computer is 0.3248, and probability that the system is empty, there is no one in the system, is 0.1218. Now, the next thing that we would like to evaluate is LQ. What is the expected length of the queue at steady state? For this, we have this formula. We know all the terms. P naught we have just computed. So, this when we substitute would give us 125 by 27, that is rho power c plus 1. Rho power c plus 1 is 125 by 27 c minus rho the whole square factorial into 0.1218, which comes from P naught, and then we have this term 1 minus 5 by 6 to the power 6 minus 6 into 1 by 6 into 5 by 6 to the power 5. Now, these terms come when we substitute here 1 minus rho by c to the power n minus c plus 1, n minus c plus 1 into rho by c to the power n minus c comes from this term 6 into 5 by 6 to the power 5. We also have the c minus rho the whole square, which takes care of the other part here. So, this would give us on substitution LQ is 1.355. So, n minus c plus 1 into 1 minus rho by c into rho by c to the power n minus c. So, 1 minus rho by c gives us this term of 6 So, this on substitution would give us a LQ value of 1.335. This is the expected length of the queue. Then Pn is the probability that there are n people in the system, which is P7, which on substitution would give us 0.068. In fact, Pn is given by lambda power 7 by 6 into 12 power 6 P naught on substitution, which would give us 0.068. Now we have lambda e, which is called the effective arrival into the system, which is lambda into 1 minus Pn. Though people arrive at the rate of 10, because some people go away, lambda e becomes 9.32, from which Ls will become 2.89. Number of people in the system Ls will be 2.89, and then Ws, which is the expected waiting time in the system on computation, is Ls by lambda e, which on substitution would give us 0.31 hours, which is 18.61 minutes. So, expected time, waiting time in the system is 18.61 minutes. Of course, as mentioned earlier, there are other queuing models. The other models would mean that we can relax this Markovian assumption. We may not use the memoryless property. We may have some general distributions for service and so on. So, right now in this lecture series, we are not looking at those extended queuing models. Now, in reality, there are also some queuing models which are called queuing networks. Right now, we do not have a network of queue. So, let me first explain what is a network of queue. If let us say we go to a hospital, and as soon as we enter the hospital, let us say there is a registration, and then we need to go to the registration, register our names here, and then come out of this and wait in another long queue, and let us say there are doctors here, and then we get served and we leave the system. Now, if you look at a little more involved system like this, there is a queue here for the registration, and whatever comes out of this queue is an input. So, the service of this is the arrival into this, service rate of this is the arrival rate into this, and from there it expands. So, this is a network of queues. So, when you have a network of queues, the analysis are quite different. We cannot assume that this arrival rate and then there is a service rate which comes in and so on. The equations are little more involved when we want to analyze networks of queues. But in reality, most queuing systems would involve more than one service or more than one server, and therefore, we may have to study queuing network models or networks of queues subsequently if we want to enrich our knowledge further in the queuing models. We can also model sometimes a manufacturing system as a queuing network. Now, say a manufacturing system may have certain machines, and these jobs may come in here. Some jobs will come here and then it goes here and then they go here, while some jobs will enter here, it may go to another machine, it may go to a third machine and go out and so on. So, the manufacturing system can also be seen as a very complex network of queues. So, queuing models have a lot of applicability, not only in day to day services like a doctor or a dentist or a petrol station or an ATM machine or a barber shop and so on. They also have applications in, for example, restaurants where you want to decide the capacity, because each seat or table in a restaurant can also be seen as a server, where the time we take to eat is the service time and so on. So, we use these kind of models to determine what should that number of tables in the restaurant be and so on. And it also has uses in things like manufacturing system, where the performance of the manufacturing system can be analyzed. Of late, queuing models are increasingly being used in medical systems, particularly in hospitals, in hospital waiting line management, trying to find out the number of doctors or number of specialists that are required and so on. So, there is an increasing use of these models, particularly in healthcare related systems, which is of recent interest to researchers and practitioners. So, with this we come to the end of our discussion on queuing models, and we wish to introduce another topic here, which is called game theory. Now, having completed the discussion for this lecture series on the queuing theory, we now move to the game theory. And in the game theoretic models, we first describe what is a game or what is a game theoretic model, and then we try and see if ways to solve the game. Now, what we are going to see in this lecture series is typically what are called two-person zero-sum games. And we are going to see solution methodologies which are based on linear programming. So, game theory can be seen as some kind of an application area of linear programming, even though if we go back into the history, game theory did not or was not derived or seen as a direct application of linear programming. The theory kind of existed before the linear programming theory was established, but once the linear programming theory was established, people could apply this comfortably to the game theoretic problems. We will only see some basics of game theory, define what is the game theory problem, and then look at a couple of ways to solve the game theory problem. So, in this advanced operations research course, game theory comes in more as an application of linear programming, because we are not going to see any more theory more than what we have seen in the two lecture series of fundamentals of operations research and advanced operations research. So, this would come in as some kind of an application area of linear programming. Now, what is this game and what is this game theory? Now, many times we are used to playing some simple games which are like two persons sitting opposite to each other and say and are betting. Now, if we take a simple situation that two people are actually playing a betting game, they have a coin, and let us say they agree that one of them tosses the coin, assume that the coin is unbiased. So, when one of them tosses the coin, if they agree that two people A and B are playing, now any one of them can toss the coin. If they agree that if they get heads, then A gets 1 rupee or B gives A 1 rupee, and if it gets tails, then A gives B 1 rupee. Now, we all know that since the coin is unbiased, there is an equal probability of getting a head and a tail, and therefore, this game will not have any profit or loss if it is played continuously for a very long period. Now, if on the other hand, now this game is an example of what is called a two-person zero-sum game, because two people are playing. It is zero-sum because what is gained to one person is lost to another, so the net is a zero-sum. So, it is called a zero-sum game. Now, let me expand this game a little bit and say that they play this game slightly differently. Now, if both of them say that each of them is having a coin and each of them does not toss the coin, but simply shows either a head or a tail. For example, they close their hands and they can put it in such a manner that when they open it, either the heads is coming or the tail is coming. They do not toss the coin, they are fully aware of what they are showing, whether they are showing a head or a tail, except that they are doing it very spontaneously. Now, if they say, if they agree between themselves that if both of them show heads or both of them show tails, A gets 1 rupee, whereas if the pair is a head tail or a tail head, then B gets 1 rupee. Now, let us try and match this game. Now, what happens is, now to express this game in the form of a small table, now I am going to assume that this is person A and this is person B. Now, when this game is being played, now A, whenever he has a trial where he shows a coin, A can show either a head or a tail. So, A has two ways of doing it. So, A will have say I would say one strategy for A is to show heads, the other strategy for A is to show tails. Now B also has similarly two strategies. So B can show heads, B can also show tails. Now there is a payoff. We said in the terms and conditions of the game that if both happens to be heads, A gets 1 rupee. So let me put a +1 for A here. We also said if both are tails, then A gets 1 rupee. So let us put a +1 here. And we also said if it is a head and a tail or tail and a head, now B gets 1 rupee, which means A loses 1 rupee. So I put a -1 here and a -1 here. Now this is called the payoff matrix for A, because this is not the payoff matrix for B, this is the payoff matrix for A, because A knows that if I play heads, he plays heads, I get 1 rupee. If I play heads, he plays tails, I lose 1 rupee. So this -1 comes here. Now this is an example of a payoff matrix, but payoff matrix for A. Because it is a zero sum game, the payoff matrix for B is automatically defined. It will be -1, 1, 1, -1, because it is a zero sum game. So whatever is a gain to A is a loss to B. So we need not define a payoff matrix for A, but for B. By defining the payoff matrix for A, we are automatically defining the payoff matrix for B. It is not absolutely necessary that this has to be only a 2 by 2 matrix. This can be even a general m by n matrix, where A may have more than one strategy, B also may have more than one strategy, and then we have a payoff matrix. So let me show a payoff matrix like this. So let us consider another payoff matrix. Now let us say A has two strategies. Now A has two strategies, which you may call 1 and 2. B has 3 strategies, 1, 2 and 3. Let us say this payoff matrix says that if A plays this strategy, B plays this strategy, A wins 3 rupees. If A plays this strategy, B plays this strategy, A wins 1 rupee. If A plays this strategy, B plays this strategy, A will lose 1 rupee and B will gain 1 rupee. Now we are also going to assume, like in the coin example, where we had this coin example, we said 1, -1, -1, 1. Now A has two strategies in this, to play either a head or a tail. Please remember that A can deliberately play a head, show a head or show a tail. Now how do we expect A and B to play this? Let us assume they are playing this for about 100 times or 200 times or a large number of times. Now what will happen is A might start by saying, let me play heads because I am getting 1 here. So A will start playing heads, and after a while B will choose between heads and tails. After a while B will realize that if A is consistently playing heads, it is unwise for B to play heads, so B will start playing tail so that B wins. And the moment B starts playing tail consistently, A will understand that A should not play heads, then A will switch to tail so that A wins. The moment A switches to tails, B will now start switching to head so that B wins, and so on. So as the game progresses, they play these strategies so many times, and such that there is some steady state gain or loss at the end of the system. So each of them would actually like to find out, in some sense, in what proportion or in what probability they play these strategies. So now A would be interested in saying, if P1 and P2 are the proportions or probabilities with which I can play these strategies, what should be the values of P1 and P2 against some objective function. Similarly, if B is going to play this with probabilities Q1 and Q2, or with proportions q1 and q2, what should be these proportions such that a certain objective is achieved. So, in some sense we have to find out the steady state probabilities with which A will play these two strategies as well as B will play these two strategies. Now, both of them are looking at playing these at certain proportions, so that they try to optimize a certain objective function. Now, obviously A will try to maximize his gain, because that is what A would like to do, and B would like to minimize his loss, because that is what B would like to do. There is a slight modification to these objective function, and this modification and some more aspects we will look at it in the next lecture.